Good morning. Remember, today is once again your guys' review, so we'll review whatever questions you guys want. Next week, you guys have your exam. I have had a lot of emails about the joys of the wonderful Lab 3 that's due today. That will be after this lecture kicked back. So it's going to be next week on Tuesday. Remember, every single one of the labs is going to have an example of it in YouTube. Go ahead and watch that and utilize that for all your information. It's going to have everything there that you can copy down and use, and that you're going to present. I do appreciate those of you guys that came in yesterday and did the lab. Hopefully you guys had a little fun doing it. And yeah, without further ado, once again, it's your guys' review. So just put up whatever questions you guys have in the chat, or yeah, otherwise, we don't have to go the full time. Give you guys some extra time just to work on your studying and obviously to work on those labs. And I will be in the office after I run a couple errands this morning. And so the lab will be unlocked. It should already be unlocked. My GA is going to be in there. And so you guys can go in and run the lab for yourself, or obviously you can go ahead and once again just use the data that you find online. So, yeehaw.
I guess we could go over the I'm a little still confused about the classes of the levers.
Okay, sounds good. So, and then Dakota, we'll get to your question. Okay, so first class lever, think your old school teeter-totter. Your fulcrum is in the middle, okay? Second class lever, you're going to have the resistance in the middle. So think wheelbarrow. You're going to pick it up on this end and the weight's going to be in the middle. Now, the way our body moves is going to be what is going to be effectively third class levers. So we've got our axis, but then we are going to be lifting an object that's at the end. So then, Dakota, remember the atlas can only do a little bit of flexion and extension. The axis is where we get rotation, lateral movement, and flexion extension. Strain, Taylor, yeah, now remember, strain is just going to be another type of potential energy. So you're just looking at the combination of how far it's moved multiplied by Young's modulus for that example. And then from there, you're going to be able to figure out the force. So the example, I think we already went through it in last time when we talked our way through. Well, maybe we haven't. Because I know you guys are probably looking at it more from the homework assignment. And with the homework assignment, we're trying to look at whether or not it was that linear relationship, or it's going to be kind of an exponential curve, or it's going to be topping out. And we were assuming it was going to be moving more upwards. So you're going to have a doubling of it with that assumption. Or even if you would have done a linear, then you would have just gone from 500 at 5% to 1,000 at 10% to 15 at 15% and so on. Okay, so for Kristen's comment about looking at the lab video, you're going to find that as you happen to be jumping, when you first lower your body down, you're not applying as much force into the ground as your body weight. That's how you're literally lowering your center of gravity. So that's why it takes a dip. And then as soon as you then push hard, that's where you're obviously going to go ahead and kick the ground, and you're going to have the force much higher than your own body weight so you can get higher. Now be careful, guys, because that video, all of the units in there is in pounds. You need to convert from pounds to kilograms, then from kilograms to newtons. So make sure you're doing that. Yeah, I guess we can do the rest of the study guide. That's Yeah, okay. So remember, with our atlas, it's only flexion and extension. Our axis is going to be effectively going to be flexion, extension, lateral versions of each, and rotation. So what do we need to do to get our discs to expand, guys? What do we need to do to get our discs to expand? Lay down. Good. What's another option? Absolutely. Hang from a bar. Or angular acceleration starts rotating at 10 degrees per second. So it's going to be rotational velocity, increases to 100 degrees per second in 5 seconds, radius of 5 meters, and mass of 100 kilograms. You don't need this. This is just there because I put it in there, and it's letting us know if you can think through what's the units you need. All you need to do is figure out your change in velocity over time. So it gives you this formula, which is going to be 100 minus 10, and then the result of that, which is going to be 90, you divide by 5. So 90 divided by 5 gives you 18 degrees per second. Angular inertia, radius is 3 meters, weighs 100 kilograms. Remember, angular inertia is simply going to equal mass multiplied by the radius squared. So 3 squared is going to be 9. 9 times 100, we've got 900. And then angular momentum is going to go ahead and be your rotational velocity multiplied by the radius squared multiplied by the weight. So 2 times 2 is going to be 4. 4 times 50 is going to be 200. 200 times 90 is going to be 18K. Now you could do this in radians, where this would be half a radian. So instead you would have effectively that 100. Just make sure you let me know whether you're using radians or degrees. Degrees for the most part are going to be easier. So who wants to give us the correct order of identifying and correcting errors and order of the skill phases? Great job, Kristen. In fact, it's so good, I am just going to go ahead, drop in, copy and paste. So what's going to be our order for identifying and correcting those errors? Now remember, think about preparation means we're just getting set. Okay, we're going to need to get ready. Windup is going to be that pulling back. So we're going back with the baseball, pulling back with the bat, where we're going to be going and effectively dropping our hips when we're going through into that vertical jump. Force producing is obviously pushing our way through. Yep. Good job, Anna and Anouk. Those are both going to be the beginning, first two. And then what are we doing? Good. So what do you guys say is the key difference between a quantifiable variable and a qualitative variable? Can't use the definition in the definition. Yeah. The way I think of it is effectively how you measure it. Quantitative variables are going to have, a ruler, a stopwatch. It's going to have something that there is a clear demarcation between each unit. Okay? Whereas qualitative variables, yes, we're talking about being more descriptive. We're not really able to give precise valuations. So in fact, Josh and Anna, from yesterday being in the lab, for example, we quantified the amount of force that was on the takeoff and landings. So when we were looking at those landings, we had one of the individuals jumping who landed incredibly hard, like put in over 2,000 pounds of peak force into the ground on their landing. And if you were watching the landing, you'd be like, oh, that was a pretty hard landing, didn't really absorb at all. However, that would be the qualitative observation. Now, quantitative is we looked at the force plates and it was just, hot damn, that is a lot of force going through the joints. And like anything else, you can get away with abuse to a certain extent. Just like you can drive your car, park up on curbs, speed over speed bumps and things along those lines, and you'll get away with it for a little bit. But eventually, that's when you're going to get a point where you do enough damage to those tissues that they're not going to be able to resolve the damage to it. So, safest position for the spine to be in if we're going to be doing some rotation. Yes. Extension, not hyperextension, and definitely not flexion. All right. So torque required to accelerate a rotating object starts at the 10 degrees per second, increases to 100 degrees in 5 seconds, has a radius of 5 meters and a mass of 100 kilograms. All right. Torque equals inertia times acceleration. Okay. Now notice these numbers are the same as we had before. So we know that acceleration is gonna be 18 degrees per second, or, you know, we could convert this into radians, but I just got in degrees. Our inertia equals 100 kilograms multiplied by our radius, which is 5, and it'll be 5 squared. So your final equation here, 100 times 25 times 18. So 2,500 times 18, and boom, there's your solution. So notice right here, guys, linear organization. So if it takes 500 newtons to compress that spring 5%, okay? If it's going to go to 20%, so we figure 0% compression, 0 newtons, 5% compression, 500 newtons. So for 20%, now we're talking 2,000 newtons. Okay. Vertical force vector for a ball thrown with 800 newtons of force in a 15-degree angle. So literally all we're going to do here is take the sine of 15 degrees, because that's going to allow us to get the y component off of the hypotenuse, and then multiply that by 800 newtons. All right, guys. When you think of sports, what movement would probably have the greatest amount of angular motion at the hips? Think about sports, what movement can you think of that would have probably the greatest amount of angular motion at the hips? Awesome. Good. Now, running's got a lot of movement at the hips, which will definitely have more than walking. However, the full angle changes will not be as great as if you see somebody who's like punting a football where they get their foot nearly where they're hitting themselves in the face with it. That's a different story. Now, what movements can you think of that have a huge amount of angular motion in the shoulders? Awesome, guys. Every single stroke in swimming, pitching in softball, javelin, not bad. Now think jump shot, you're only going from here to here. You're not really moving the shoulder that much. But softball pitch, now we're talking about 360 degrees of rotation. Swimming, same type of thing, 360 degrees of rotation. Throwing, you know, because we're going out and we're coming in, we're probably having 180 odd degrees of rotation. But it's probably gonna be that softball pitch or swimming would be the highest that we're gonna find. So now we're talking about, remember the different cervicus, capitis, and then even the hyoid muscles, SCM, pulling ourselves forward, lumbar extension. Now we're talking about our spinal erectors, multifidus, etc. Lumbar flexion. Now we're talking about our external oblique, our rectus abdominis. Trunk rotation. Remember, these are definitely going to be our obliques, and specifically how our external on our left side and our internal on our right side is what's going to turn us to the right, and vice versa, as the angle of pennation. Okay, so then a lever formula problem. So force needed to produce on a lever resistance arm of 0.9 meters and 35 kilograms of resistance, and the force produced is 50 kilograms to keep this in balance. So notice we're setting it up so we've got 0.9 times 35 and then 35 times 9.81 so we can have newtons. You could omit the times 9.81 on each side if you just wanted to save yourself the time and energy, but I got it this way. So once you factor it, you've got the lever arm of 0.9 times 35 times 9.81 divided by the sum of 50 times 9.81, which is going to equal our lever arm itself. And that lever arm itself is going to be about 0.63, 0.64 meters, because it's only going to be at 70% of the length of the other side. Okay. Where are we going to have angular motion in an athlete that's swimming forwards? Yes, and? Yes, and? Mm-hmm. Mm-hmm. Yep. And probably even the head a little bit too. So pretty much everywhere. Done. However, where is the linear motion in athletes swimming forward? The linear is actually just in this body's center of mass. So with anthropometrics, guys, we're now talking about lengths, mass, circumferences, sizes, okay? It's not gender, it's not race, it's not religion, it's not any of those things. It's just what can we actually quantify? CSA is cross-sectional area. Why force vectors matter? Because it allows us to figure out vertical and horizontal forces and how those in turn are going to be influencing the forces that not just are we applying to the object, but obviously to our own bodies. And like anything else, we've got certain capabilities to produce force. One of the, I call it fun, but I don't know if you guys would agree with me, which is if you look at the coefficient of friction between shoes and the floor, you actually learn there's only such a certain level of steep angle that you can actually push off the ground where you don't have enough mass going down into it. So you actually would naturally slip and fall. So what this effectively means is you can only change directions so quickly. You can only move so fast. Like whenever I watch my cats, or even on occasion, Norbert trying to haul off against something, and we've got laminate floor that we laid throughout the house. And so you'll see them just burning out with having no traction because they're putting in too much of a horizontal component, but not enough of a vertical component to actually still keep traction. So they, in effect, just sprint to nowhere for a couple seconds. So it gives us an idea of effectively how things are going to move. Why is spin important? Because that's going to influence the essentially how things are going to, well, how okay. Now we're talking about the different movements of the scapula. There's a lot going on here, guys. We've got retraction, protraction. Then we've got effectively upward and downward rotation. We also are going to have effectively elevation and depression. And remember, it's going to all link to the different movements that we're doing with the arms as we're going through and doing different exercises. So keep in mind all of the different muscles that are going here. I would thoroughly suggest you guys write that out and chart it together so you can see what's going on. And my answer to the final question, which really we're talking about doing force vectors. And that's the entire study guide. Woo. Is there anything else you guys would like to review?
I have just two questions. It's not about it's about the test. The math only part, only one person has to turn it in the group, correct? Or am I wrong?
Yes, for the exams, good question. Next week, you guys are gonna have the individual exam, you obviously take it on your own. Now the group one, both the math only take home and obviously the no math, take home group exam, you only need to take it once as a group. In fact, it would make life a lot easier on me. So I highly, highly suggest.
And another question. I was looking at the syllabus. Is the final comprehensive?
Yeah, it'll be comprehensive, just like this exam has got some elements from the first exam as well. Remember, guys, your education is not drawing on an Etch-a-Sketch. So you make the drawing once, then you shake it and make it go away. Instead, the idea is we're more of trying to build a building of knowledge. So we're trying to constantly keep adding bricks, and we need to make sure the foundation is still solid. So go ahead, Dakota. If you got any other questions on yours, you can feel free to go ahead. And that, guys, is just that link to the wonderful bone part. Okay. So attachment angle 86 degrees, holding a weight that is 25 centimeters from the elbow, that weighs 20 kg, and the arm center of mass is at 12.5 and weighs 5 kg, along with the attachment of the bicep is 2.5 centimeters from the elbow. Okay. So let's go ahead and draw this bad boy out. Okay, so our initial formula, when we talk about force times force arm equals resistance times resistance arm, is going to give us effectively force, which we have no idea what that is, multiplied by, we're going to go ahead and we can do all this in centimeters since it's all in centimeters. So we can say just simply 2.5, okay, equals, now we've got two parts here. We've got the resistance, which is going to be 20 kgs times 9.81 for gravity, and then multiply that by 25, okay? Ooh, I wrote that like I was European. Then we're going to go ahead and our second component here is going to be 5 times 9.81 times 12.5. So from there, we'd factor it into our force equals, and now I'm putting my order of operations so you guys can see it and know how to do it. 20 times 9.81 times 25 close plus open 5 times 9.81 times 12.5 close and then close the other bracket divided by 2.5. Okay. And then that's only going to give us the answer for just the vertical force component. So we take this final F that you solve for right there, and our actual bicep force is going to be equal to that F value divided by the sine of 86 degrees. Because when you're thinking it through, and you're, once again, feel free to obviously draw it out, this is pulling down and this is pulling way down. So hence, this is the negative side, and that's going to be our lifting side. Any other questions you guys want to go through? As the angle of the facet increases in size, it's going to be able to deal with a greater amount of force absorption. And let's go ahead. The answer you're looking for that one is right here. So it hits the ground after 2 seconds, a total of 50 meters away. So we're assuming it started on the ground if it hit the ground there. Okay. So that means its horizontal velocity has to be 25 meters per second, because 50 meters in 2 seconds. Now the vertical velocity, when we use the vertical formula, okay, well, it had to be in the air for 2 seconds. So we need, once we solve for the vertical velocity, has to be 9.81, because it went up for 1 second, down for 1 second. Math goes really easy. So to figure out our angle, we're just simply going to take the inverse tangent of 9.81 divided by 25. Yeah, we went through that one also on Monday, which is, remember, it's just moving inferiorly. They're lowering their body. When we're looking at the center of gravity change, when you're going from standing up into being in a 2-point stance. Any other questions you guys want to work on? Okay, so remember, guys, you can use the video online. You can come by the lab and do it that way. All of the labs are already recorded and online on YouTube. It'll be under the fall 2020 classes. You just got to look through, find them, watch them, use them. That's it. Everything else, obviously, you know, if you guys are able to come to campus and do it, plus I think it's obviously a little bit better if you can do the hands-on and kind of see how things work together. Otherwise, you know, take care of yourselves, keep studying for your exam, be ready for it, and we will go. There is a couple torque questions, so that doesn't really narrow it down. Referring to this one here. Yeah, no class on Tuesday, guys. You guys just got your exam. Yeah, so torque equals the inertia times acceleration. So you've got increases from 10 degrees to 100 degrees in 5 seconds. So changes 90 degrees in 5 seconds. 90 divided by 5 is 18. So that's where the 18 comes from right here. That's acceleration. Radius is 5 meters. Mass 100 kilograms. Inertia equals mass times radius squared. So 100 times what'll be 25 times 18 is going to give you your total torque required. Yeah. And like guys, you can always review the videos because we've gone through everything, literally everything on the study guide. I still think it's better if you try to do it on your own and then you come and check your answers through this method. But you guys got everything you need. You know, go through your lecture notes, go through the lectures, and obviously be ready that the study guide is not going to give you every single question. You are going to have to think your way through some things, apply your knowledge. And I would be lying to you if I said it wasn't challenging in its own way. So if there's no other questions, we'll let you guys get on your merry way early today so you guys can focus on studying for the exam. Make sure you work out what times are going to work with your group so that you guys are going to be able to take the exam, obviously within the times needed on Tuesday, or just, you know, during early next week. And then on Thursday, we will come back and we will get after it. And then we're going to start talking about the lower extremity and then some functions of muscles and tendons and otherwise, which will hopefully be a good time. So any other questions, comments, concerns before we call it a day? All right, since I'm not seeing any, you guys stay safe out there. Thanks for swinging by and asking some questions on how we can help you guys out so you feel good about the exam. And I will see you guys next week. So stay safe out there. Bye-bye.